go a little bit back where you just show us what the data set is and what we intend to do so that we understand what you are doing.
All right. Thank you very much. And good morning, all. I hope you are all in the morning session in our various areas or in our various locations. Just a quick recap. Last or day before yesterday, in our last lesson, we walked through data for machine learning, which was built on the earlier session by Dr. Shamsu. We see how we can do some data wrangling using Python. And of course, with the help of scikit-learn, you see the various type of data. We also see how we can remove the empty spaces in our data. We see how we can inspect our data, both the rows and the columns, that's the headings and the data records. We also see how we can use string expression to extract some particular data that we need. We also dwell briefly on normalization, whereby from there we are able to move straight to linear regression. And on the linear regression, on a lighter note, we compare it with the polynomial regression. However, on the linear regression, we see an example of how to make prediction from a dependent variable and of course independent variable, whereby we see how we can compare or make prediction based on month using month and price. We also compare months. We also see the variation between using month and price versus using day of year and month, whereby we also explore various plotting to see how these various variable correlated with each other. Also from the correlation, we also see how a perfect correlation should be from the data point. We also touch briefly on the formula whereby we say each an individual should go and dwell deeper on that. Well, for now, you don't need much of the mathematical aspect. And of course, we are able to correlate the the price and day of year. After we realize that day of year have more correlation than month. And this is the logistic line that we are able to, the linear logistic line we are able to plot. And today, we are going to see another type of linear regression, which is polynomial regression. The polynomial regression is actually built on the linear regression. However, the polynomial regression is here to see how the straight line, the linear regression is normally straight. However, the polynomial regression is being bent a bit. If we try to bend the line a bit to suit how the data moves around. But to achieve that, some of the variable may be squared, or in other cases, some of the variable may, the volume of the variable may be, you may need to take the volume of the variable. And taking the square or volume or fourth square of any variable, hello, just a minute, please.
Yeah, before Said continues, so you remember we are talking about logistic regression here, polynomial. Hopefully tomorrow we'll be able to also cover logistic regression. Today is polynomial regression. So this is still predicting real numbers, predicting like 1, 2, 3, or 0.1, so real numbers or continuous value. But tomorrow we'll be able to see the other type of regression, which is called logistic regression, which can be used for classification, binary classification. Um, yeah, so polynomial regression is, we can see, simple linear regression is simple. From the name, you can see simple. It can fit, a very simple linear relationship, but polynomial regression is more complex. As you can see from here, polynomial regression is fitting the lines, even though they are not straight, right? You can see the lines, they are not straight, right? But the polynomial regression is trying to fit them, to connect them, to make relationship. So in essence, a summary is that simple linear regression can be used to fit, relationships that are simple, that are linear, but polynomial is more complex model. Why is complex? Because it's complex because it can, try to, get a model relationship between variables that are not even, linear, simple linearly connected. So this is one of, okay, Saeed, are you back?
Yeah, yes, I'm back.
Okay, okay, go on.
Thank you very much, sir. And thank you for the explanation. Yes, this is just the difference between the two. However, polynomial regression normally have power of 2 and above, power of 2 to n. You see the independent variable sometimes will have power of 2 to n. This one can be b2 x1 raised to power 3 plus b3 x2 x1 raised to power 4. Please let's note that this x is still the same variable. However, the power may be 2 or above. That means square regression is also a part of the polynomial regression. However, putting it into practice, we still employ this the scikit-learn processing and of course the polynomial feature. To use these features, we need the help of yet another scikit-learn library known as make pipeline. This make pipeline from this diagram help us to stack various aggregators. It helps you to create a more complex model. Like this polynomial feature is coming in to help you get a polynomial data encoded. However, still you need the last part of the pipeline to be what? To be linear regression. If we can remember, in the beginning of this lesson 4 that Dr. Shamsu walked us through, he said machine learning can broadly, under supervised learning, can either be regression or classification. As we can see here, the last part of the pipeline will either be a regression, that's for prediction, or classification, that's classifying a particular set of categories. So with this pipeline here that you are calling, make pipeline will now take in this polynomial feature and the linear regression at the end. And lastly, we use the pipeline to fit the X train and Y train here. We already know what our X train is and what our Y train is. And for a quick recap, you can inspect the X train. X train dot should we use dot head? Oh, I think we have already converted it to array. Okay, so this is our X train here. And our Y train is Y train, which is the label. This is our Y train here. So now, to make our prediction using the pipeline, we run this, still using the mean square error, and of course, to check how good our model is. We will see that this curve here is slightly bent. We see that we have a curve, we didn't have a straight line. The curve is trying to move towards this data point. because logistic regression, polynomial regression still will also use a line to find a way to fit into all these data points. Having this is still very hard for us to know whether it's better than the linear regression. However, with the help of this mean square error, we will know whether we are making progress or not. You can see that we have 2.73 here for the polynomial. If you can recall from the linear regression, what was our mean square error? Oh, this is the mean square error for the linear regression. We have 2.77. So if you compare 2.77 and 2.74, which one is better? The audience, please. What? Yes, who is on the line, please? Hello, whoever is talking, we can't hear you.
Hello? Okay.
Yeah.
Okay,
So
better.
2.77.
2.74. Exactly. Yes.
7.4.
Exactly. So we see that the linear regression gives us 2.77, while the logistic regression gives us 2.74. Since we know that mean square error, we try to minimize mean square error as little as possible. So having 2.73 means that, yeah, this linear regression is better than the, this polynomial regression is better than the linear regression. However, difference is not much. So for this is just an introductory class, or should I say session, to the polynomial regression. However, we can still dig deeper into our data set to see how we can encode the data to have a better performance.
Yes,
One,
Said.
yes.
Yeah, yes. So in machine learning, just Said, he said you can deep, you can dig deeper when you are given data or anything you want to do. Your intention first is to, run a simple baseline to see your algorithm performance. So for example, now we run a simple baseline where we see we have mean square error, which is 2.7 something, or one, I don't know. So then you say, okay, this is the error. Now, how can you improve the algorithm, the performance by doing some what we call future engineering? You try to, model some future to do. So for example, if this prediction that we did, we have like 7 columns. So you can try back and see how can I reduce these columns to make sure I have better, futures. I think we can discuss this maybe in the future lessons. This is something big in machine learning, which is called future engineering, meaning how can you select the best future to train your machine learning model? That is one a big disadvantage of machine learning. Machine learning, one of the big disadvantages of machine learning is that you need to engineer the future. You need to tell the machine learning algorithm, these are the futures I want you to predict. Different from deep learning. Deep learning, you don't tell it the future. Deep learning is the oga kwata kwata. Deep learning automatically determine the futures to create prediction for you. That is why people are now moving from classical machine learning. So this is what we call classical machine learning, using giving algorithm futures. I say, okay, I want you to predict a house. Then I say, okay, but the house has the, this room, the house has, it's located here. These are futures. Then you give it to the machine. Then you need to engineer the feature to select the best feature. So this is something in machine learning. But when you move on to deep learning, which we will cover after our machine learning session, for those of you that are interested that want to continue, in deep learning, you don't need features to engineer the features, which is a big advantage that you don't need to spend much of your time trying to get future engineering, because future engineering is a big area, even with books. How can you create best future for your machine learning algorithm? Yes, you can continue, Said.
Thank you very much, sir. So still on the feature engineering, we will now look deeper into our data. Just a quick reminder, we'll note that we are using just the pi version of the categories, of the varieties, I mean, for this prediction. However, for us to consider other types of varieties here, for now we are using just the pi type. However, we want to see how we can use these other types of varieties to make the prediction. However, this type of variety is one of the aspect of the feature engineering that was spoke about. We call this type of data categorical data. If you can take a quick refresher, earlier on, we say we have two types of data. Some data are quantitative, that's numerical, while some are qualitative. Now that you have some pumpkins that can either be Big Mac, blue type, Cinderella, etc., up to pi type, you will find a way to see how can you encode this data so that the machine will understand. And we know basically, even in computer, machine prefer to have ones and zeros. So this particular feature can be encoded in two ways. We can use two ways to encode this type of data. One of the way, for example, let's say you have a data that have a particular column called color, and you have red, yellow, green, and yellow here. So for you to encode this type of data, you can using one hot encoding. Each data point, if it is red here, it's only red that will be one. The other columns, or should I say the other data points, the other cells are going to be 0. Same red, the red will be 1, the other cells will be 0. While yellow, when it's yellow here, you see yellow, then red will be 0 here. Only yellow will be 1 and green will be 0. And when it's green, only green will be 1, the other will be 0. And if you have another yellow here, if another yellow is coming here, then it's only this center that will be 1. This will be 0 and this will be 0. This is called one hot encoding. The opposite is 0 hot encoding, whereby the particular data point will be 0, this will be 0, and the other ones will be 1. But the mostly used is the one hot encoding. This is one way of what encoding our data. Let's say we have red here as colors. Let's define a class here, an array here, colors. And we want to one hot encode this. Our data is going to look like this. Sorry, pardon me. Let's say this is the color. Using one hot encoding, it's going to look like this. You can use this particular formula or a particular library called get dummies of pandas class. It will help you to encode the colors. Let's now say our color I'm still using this color array, or let's say the color is more than let's now add another color. Let's say maybe blue here. If you have a blue as color here, if you want to one hot encode it, you'll see that blue is here now, right? But the color, based on the arrangement, which one comes first? Red, right? You have red here. So red is going to show up here first. It's only red that is going to have 1. all the other columns are going to be 0. When it is yellow, it's only yellow that is 1. All the other colors are going to be 0, etc. So this is called one-hot encoding. The other type of encoding that we have is called label encoding, in which all the variables are going to be given a number starting from 0, 1, 2, 3, 4. Like example, if you want to encode this one, red, yellow, green, brown here, you'll see what it's going to give us. It's going to tell you that this red is 2, this yellow is 3, this green is 1, and this brown is 0. For me, this, you can notice that it is encoding them alphabetically because brown comes before green. That's why it's giving brown the 0 encode. So if blue should come here, so blue is what? Is now 0. Brown is now 1. Green is now 2. Yellow is now 4, while red is 3. You see that Y is the last alphabet. That's red. Red comes before yellow. So these two types of encoding methods are the popular encoding methods that are being used in machine learning. Of course, in some deep learning aspect. Please, any question before we now use it for our training? All right, I want to assume you all understand it or the opposite. I hope we all understand it. So now back to our pumpkin example. Our new pumpkin variety, we now want what? Using this get dummies, that's, we want to use it for the what? For the one-hot encoding, right? Using this for the one-hot encoding, this is going to what? Change all those pumpkin types. The fairy tale, miniature, head, and this pie type is going to convert them into what? One-hot. We see that when it is pie, it will all have 1. And the moment it's now miniature here, we can see that it's miniature that is 1, and the other columns are what? Are 0. We can inspect the whole head of the pumpkin and see, okay, this is the initial new pumpkin, right? So let's now, yeah. So here now, we are now trying to what? To one-hot encode all of these variables and create our training data set. Now we now want to create our training data set. We'll see that this variety is now being one-hot encoded using this method. Month is maintaining its usual number, that's between 9, 10, 11, 12, right? Then city, you'll also notice city2. Under our data, yeah, city name here. So the city name here too, we are what? We are encoding all the city name. St. Louis, San Francisco, from what? From Atlanta to this. We are also what? One-hot encoding it here, city. And lastly, we are also one-hot encoding dummies here. And we are joining it to create what? The X input data future. And the Y label is what? Price, which is what we are trying to predict. So when we create something like this, and let's inspect the last, you have X now. Let's see what X will give us. We now see that we now have X with what? With our newly created one-hot data using one hot encoding, you see that when the city is miniature, it's only this one, we only have one here, and all the other cities have zeros here. Sorry, the type of pumpkin. This is a type of pumpkin. The first 4 columns are the type of pumpkin. While here, month still maintain its all these are September. I want to believe 9th month is the September, while cities too are all one hot encoded. You see that all these cities are zeros, except what? Of course, St. Louis. It's St. Louis that is what? That is the city. So all the other cities will be what? Will be 0. Whereas also the package type, this Bushmail, this 119, is only this half Bushmail carton that is what? That is active. So the other ones will be what? Will be 0. So we are now using how many features? We are now using 4 features now: variety, month, city, package. And all these are now what? Are being one hot encoded, except of course the month. And our what? Our label is still maintained. It's so what's our label? Why? Let's see. Dot till. So let's see our label as well. All right. This is the label of this what? Of the data above. This is the tail, the last part of the label, and likewise, this is the X tail, the last part of the what? Of the input data. Now we've seen that we need a polynomial aggregator and linear regressor for making the prediction. We've also seen that our data too is ready, whereby we are using 4 features and we have one hot encode most of the features with one hot encode 3 of the features, and month still maintain its feature, its original state. Now we want to train a model. Training this model now, you now see what we have is what we are doing next. So after running this, of course, with the help of the pipeline, we can now see that we have what? Mean error of what? 2.48. We have mean error of what? 2.48, and this model determination of 0.95. Good. So what can we notice here? We see that we have some level of improvement. Is that also? I hope you are together. You will see that now we have mean error of what? 2.48. The last best performing mean error we have was 2.74, if I'm correct. And now we have an improvement of what? 2.48. You can see how this feature engineering have also helped us in what? Getting at least something from it has given us less error.
Can you hear me, Sahid? Sahid, can you hear me?
Yes.
Okay. So I have a question. So my question is, some of us may ask, why are we using this MSE, mean square error? So some people may say, okay, in some machine learning, we can use accuracy. So why are we using this MSE? So can you tell us? So I believe the reason why is, if it is regression, we have a way to measure how good the algorithm is. If it is classification, we have a way to measure how good the algorithm is. So can you elaborate why we are using MSE, not like accuracy?
Okay. All right. Thank you very much, sir. I think you have already given the answer as well, because mean square error try to work with this data point, right? This data point, it tried to what? Let me just take you all. Yes, it tried to take what? The mean square of the error between this point. However, if you are going with classification have its own measurement of accuracy separately. You can use maybe F1 or accuracy to measure for classification. However, for regression, which is for prediction and uses a data point like that is mostly in linear fashion or polynomial fashion, that's usually this line, try to measure this distance of this error. I hope I'm together. I hope you are together. I don't know if anybody have additional explanation to that.
No. That's just I want to just point out that because we are using regression, that is why we are using MSC. Just to explain. Yeah, thank you.
Okay, thank you, sir. Any additional question, please?
Sir, yes, sir.
Let's go ahead, please.
Yes, sir. Sir, on mean square error, sir, is there any standard value that, for example, if we reach, we can't use, for example, if the MSC is 0, let's say 5, for example, we can't model it. For example, if it is reached like 5, we can say that we can't model it. Is there any standard value for that?
Well, I will say that if you say 5, mean square error usually is like in percentage. Like here, it comes in percentage. Like here, we are having 2.48 is like 9.1%. It's trying to tell you that the error that you have here is about 9.1. However, what we are looking for like 0.0 something, maybe 0.002. The smaller the mean square error is, the better your performance. So when you now have 0.00, it means you have a perfect model, which is nearly impossible. When you have 0.00, that's when we can say that machine learning have fully achieved human maybe intelligence. Maybe they can even be more intelligent than humans. I think, in fact, that's what most machine learning, deep learning researchers and practitioners, industrial practitioners are working towards, to reach this 0.00. So whenever you create a model, you have to tell your audience what is your error or what is your accuracy. If it is classification, if it is regression, you have to tell them what is your error, so that they know how to handle your application. Like this application, if you say it can predict the price and you give to a client that a client can use it, and the client use it to make prediction, and it gives the client maybe an error. So the client is going to catch you and say, you told me that this thing is working fine, but what happened? But I didn't mean you told the client that this is the error. It's not all the time that this prediction is correct. I have this number of error here. So the client will put it at the back of his mind that this is what you have. I hope that answers your question.
Yes, sir. Thank you.
All right. So now, still, I want us to take another
I have another question,
example.
Said. I have another question, Said.
Okay, sir.
Can you go down? Can you scroll down this code? This code. Okay, yes, yeah. Yes. Okay. So can you explain here, for example, here we calculate mean square error where we have MSC the result, and here we calculate a score between X trend and Y trend, right? Here we calculate a score between X trend and Y trend, and here MSC we calculate the mean square error between Y test and PRED. Can you tell us like what each one means, and yeah, just more information on that? Can you?
Okay, sir. Okay, let me try and see. I think this model determination, though we've not been focusing much more on it, but we've seen it briefly in our previous lessons. This model determination is trying to show the correlation. It's trying to show whether we are making progress if we maybe let me see. Let me take us back a bit. There's a place we yes. Let me take us back a bit here. In our linear regression, we also calculate the score. This model determination, what? 0 means it doesn't take input data into consideration. When it's 0, it means the data set or the combination of data you are putting into the model have less importance to the model itself. But when it's very close to 1, it means your data is making sense. It's sensing some correlation between your data. That's why when we did our first test using some random variable here, using just the which one did we use there? Just the day of year and price. Just using day of year and price to make the prediction, it gave us this model determination of what? 0.44 here, 0.04. You can see how far it is from 1. When it's 0, it means you are having poor data engineering. And when it's very close to 1, it means you are what? You are doing good, or your data is making sense. You can see how close this is. I don't know whether there's additional explanation. Okay. So with that said, I want us to just explore deeper using what? This label encoding. Here we use one-hot encoding to input our data. However, why not let's try to use what? This label encoding here to extract our input data. Let's say we have this. Let's see our x dot maybe head. So now, using label encoding, we can see how our input data will look like. This variety, when we have 3, it means it should be around either pi or one of these stuff here. Okay, this is using one-hot encoding. This is how our input looks like, the tail. So when it is miniature, it will just put 3. It will just give this heading as what? As pi type or variety. Miniature will be 3. Maybe pi will be 4. The month maintained is what? Is input. The city as well. The city, which city is 1 here? Let's compare it. We see that we have which one was marked 1 using one-hot encoding. We see that it's St. Louis, that is 1. All the other ones are 0. So St. Louis will be what? Will be 1. Then any other city will have different label. And the package, the first package will be 0, the next package will be 2, the next package. Okay, let's try to see the tail to see how we can compare this. Let's note what the head looks like, and then let's see what the tail will be like. You see the tail variety is 1. The city now we have 99. We notice that under the data set, this city, we have so many cities, I think about 10 cities or 12. So this makes sense to give that particular city number 9, starting labeling it from 0, and we have package here. The second package, of course, the 2 will be any of this package. Is that also? To be any of these Bushmail packages. You know, we are only working on Bushmail. So having this as our data input. The y input will still maintain its status. So now let's use it to train this model. Every other things will be the same. And of course, everything being equal, let's run this and see what we have. So running this is what we have. We have our mean error to be equal to what? 4.24. And our model determination is what? 0.84. Can you see that? Are we making progress or we are regressing?
We make progress.
Are you progressing or regressing?
Yeah, we are making progress.
In what sense? Can you explain that?
The percentage of the error is getting higher.
Yeah. And so what does that mean?
I mean, like you explained earlier, it's like when the mean error is getting lower, I mean, the percentage, that means the model is performing good, right? If I understand, but I don't know.
Okay. Yeah. You just hit the nail on the head. So here, having 4.24 compared to what we have here, which is 2.48, we are not actually making progress in terms of performance. So that's why during feature engineering, you may try this particular way. It may give you a good result, but making one or two adjustments may give you a different result. So sometimes you have to try all these aspects. So if you now try this label encoding and you have this particular result, if I'm the one, I will have to reverse back to this. I will say, okay, let me just use my one hot encoding gently and go, because this is giving me a better performance. However, you may now use another feature here among these columns, but then now come and test it on this both one hot encoding and the label encoding. You may be lucky that this label encoding may give you a better performance in another aspect. But as data scientists, we need to have all these skills handy. We need to have all these tools handy to see that, okay, we can encode this different way. And of course, some people will say using label encoding sometimes confuses the machine, even though 0, 1, 2 up to the number of the labels, while some used to have better performance using it. So depending, machine learning, you need to have the skills as well. You need to practice different methods. And of course, there are other methods like hyperparameter tuning. We are going to see those in the deep learning aspect. When we start using RNN, GRU, and of course, attention, in which you are going to see how we'll be interchanging the hyperparameters until you have the one that give you the least error. So those one that you have the least error, all these big papers that you are seeing, they have to pass through all these stages. It is the one that give them the least error that they will report on the paper, but they will not tell you that they tried it maybe 1,000 times before they get that particular performance. However, this is just one aspect of the trial. So the more you do the trial, the more you have this machine learning skills. Of course, I know Dr. Shamsu will give us more insights on this. I can remember when I was also facing some challenges, I have to reach out to him to see how I can also solve one or two problems using deep learning. Okay, I think this is the end of our lesson. This table also compare all the performances of all the trials that we did. Some of them we didn't even do it, but you can see how the performance are being compared. I hope you can check it out and compare it with the codes. And thank you very much. I don't know if there's additional explanation or comment or question.
Okay, thank you very much, Sahid, for this discussion. So today we finished looking at, the linear and polynomial regression, which can be used for predicting continuous value. Hopefully tomorrow, I myself, hopefully, I will be able to do the next one, which is logistic regression, which is used for classification. I hope I will get time to look at the notebook because I have many tasks, but hopefully I will be able. Don't forget to come tomorrow for us to finish the this session regression, and then next week we can start looking at classification. Let me think. Okay, so I think okay, we have some questions before we go on. Raise a question, but before we go on, also I would like to show us something. But let's attend some question. Can you go on with your question, please?
Assalamu alaikum.
Assalamu
Hello,
alaikum.
Assalamu alaikum.
Yes,
Hello?
we can hear you. Go on.
Okay, yes, sir. Earlier you passed an argument of 2 or polynomial regression. Could you explain more, please, sir?
Okay, thank you for that question. So this 2 is just to square the input of the day of year. This 2 is to take the what? We are taking the square of the day of year. Yeah. Yes, here we are squaring the what? The day of year as a variable for the first test, and it also square the other additional variable that we have. And that's what gives it this polynomial capability, these 2. So if you pass 3 there, it means you are what? You are taking the cube. These are also another way of what? Checking. If I'm you, I can just pass in 3 and see what the performance will be. Some can even pass in 4. I hope you are cleared.
Yes, I'm clear. Thanks.
You're welcome.
Assalamu alaikum.
So my system will soon go off. Go ahead, please.
Yeah, I want to know if it is possible to create like hybrid model. For example, if you have like model A of that will be predicting wind direction, and also you have model B for, let's say, predicting high temperature. If you think, for example, can you make it like hybrid to